something we know is when particles are put next to each other that have a charge, that have an electric charge, for example, a positive or two positive particles, we know those particles are going to want to move away from each other. We also know if there's a positive particle beside a negative particle, those particles will want to move closer together. So those forces that cause those particles to move, we call those electrical forces, Fe. And the purpose of this lesson is to determine what those forces actually are. So the equation that helps us determine this is called Coulomb's law. And the equation is K, Q1, Q2 over R squared. This should look a little bit similar to Newton's law of universal gravitation. Hopefully you see that. And it's interesting that these two forces, the electric force and the force of gravity, behave very similarly in a lot of ways. In this case, the variables are a little bit different, but they're very similar. So K is a constant, just like it is for Newton's law of gravitation. And in this case, the value of K equals 8.99 times 10 to the 9. And the units for this are Newton meters squared per Coulomb squared. So that's what K is equal to. So when we use this equation, the other things we should use should be in newtons, meters, and coulombs, and we'll see that in a second. The Q's are the charges of the two particles. So Q1 is the charge of particle 1, Q2 is the charge of particle 2, and charge is measured in coulombs, right? Just a quick refresher on what a coulomb is. A coulomb is actually the charge of 6.241 times 10 to the 18 protons. That's what 1 coulomb is. It's just like a group of protons equals 1 coulomb of charge. And if we take the reciprocal of that, we know the charge of 1 coulomb, the charge of 1 proton, if we just do 1 over that, is going to be 1.6 times 10 to the negative 19 coulombs. So you can see 1 proton has a very small charge in terms of coulombs, but so it takes a very large number of protons to make a coulomb. And the other thing to note is that protons, notice how I said protons. 1 coulomb is a certain number of protons. If we were talking about electrons, we would say the charge is negative 1 coulomb. So negative 1 coulomb is the same amount of electrons, because an electron and a proton have the same electric charge, they're just opposites of each other. So negative 1 coulomb is 6.241 times 10 to the 18 electrons. Okay, so electrons are negative in terms of charge, protons are positive. So that's what the Q's are in the equation. And then the R squared, the R is just the distance between those charges. Again, sometimes R is used, sometimes D is used. R just stands for radius, basically, like the radius between those two things. All right, so that's Coulomb's law. The next question asks us how it's comparable to Newton's law of gravitation. I'm going to leave that for you to think about. But the key is, look at this constant. Compare this constant in the electrical force equation to the constant that's used in Newton's law of gravitation. That should tell you something about the relative strengths of those forces. Okay, so if we were asked to calculate the electric force between two charges, what would it look like? So if both the charges are 1 coulomb, that's not bad, right? So Fe is equal to K Q1 Q2 over R squared. So we know K is 8.99 times 10 to the 9, right? That's our K value. Our Q1 and Q2 are both 1 coulomb, as per the question. And we're going to divide by 1 meter squared. Notice how I didn't put units, and I didn't put units because everything is in the standard units that are going to work for this. Remember, for the charge, we need coulombs, for the distance, we need meters, and K is already in those units. So if we do this calculation, you should see that it comes out to 8.99 times 10 to the 9 newtons. Is that a big force? That is a big force. What is that? That's almost 9 billion newtons, right? That's a lot of force between two charges. And those charges are just 1 coulomb. It turns out 1 coulomb is actually quite a lot of charge. So it makes sense that this force, and they're not very far apart, so it makes sense that this force is the way it is. Now, question, what direction is that force in? So if we have two 1 coulomb charges, and 1 coulomb charges, separated by a distance of 1 meter, oops, what direction is that force in? And the key here is to realize, both these charges are positive 1 coulomb. They're both positive charges. When they're positive charges, we think about the direction of the force being away from each other, right? Those two things are going to want to get pushed away from each other. So the direction here of the electric force is away from the other one, and this one is away from it as well. These forces are going to be equal and opposite each other, same as the gravitational force, but in this case, they're pushing away from each other. Okay? All right, next. What about if one charge is 1 coulomb and one charge is negative 1 coulomb? Well, we can do the same calculation. It's going to be the 8.99 times 10 to the 9 times 1.0 times negative 1.0 over 1 meter squared. So notice how the force this time is just going to be negative 8.99 times 10 to the 9 newtons. So when we get this, when the force ends up being negative, this is the other case where we have a 1 coulomb force, or 1 coulomb charge, I should say, and a negative 1 coulomb charge. They're going to want to be attracted to each other, right? And the way that shows up in the math is when the force is negative. So a negative force for the force of electricity means that the force is attractive, it's towards each other, and a positive force means they repel. I will discuss the electrical field in another video. So let's move on to these questions. I'm actually going to make the units for all of these questions microcoulombs. So I'm going to put a little mu symbol here to stand for micro. And just so you know, 1 microcoulomb is equal to 1 times 10 to the negative 6 coulombs. So micro means millionth of. Like a micrometer is 10 to the negative 6 meters. A microcoulomb is 10 to the negative 6 coulombs. So I made the charges much smaller to make the question come out a little bit better. And so basically we have 3 microcoulombs. We have negative 2 microcoulombs. And we have negative 1 microcoulombs. And the distances between them, I've made those 3 times 10 to the negative 5 meters and 8 times 10 to the negative 5 meters. All right? So we want to find the net force on Q. So let's think about this. What forces are going to be acting on Q? If I draw a free body diagram of Q right here, what forces are going to be acting on Q? Well, first of all, Q is a negative charge, so it's got more electrons than protons. Q1 has a positive charge, and Q3 has a negative charge as well. So what are going to be the forces on this charge? Well, we know so Q1, there's going to be an electrical force between Q1 and Q2. And think about it, is that going to be an attractive force or a repulsive force? Well, it's going to be attractive since they're opposites, right? So we're going to have a force going this way, and that'll be the force of Q1 and 2, right? And then we have a force from Q3, between Q3 and Q2, right? And there's going to be a force there as well. Is that going to be repulsive or attractive? Since they're the same sign, they're both negative, they're going to repel each other. So the force on Q2 is actually going to be in this direction, right, from Q3. It's going to push it away from Q3. So we can see in this case, both forces are actually pushing in the same direction. So that thing is really going to accelerate if we let it. So how can we calculate the net force on Q2? Well, we just need to calculate those two separate forces, right? I think you can do that part. So pause the video here in a second, and then you can check your answers when you unpause. So these are the two forces that I got. Force between 1 and 2 is negative 8.42 times 10 to the 6 newtons. Force 2, 3 is 2.78 times 10 to the 6. So it makes sense. Remember we said it's attractive force between 1 and 2, which is why it comes out negative, and repulsive force between 2 and 3, which is why it comes out positive. The sign here doesn't necessarily indicate the direction. You just need to think about the direction yourself when you're doing a problem like this. So the net force, that's what we're actually asked for, is in the same direction, right? So well, each force is in the same direction, so it's going to add up to give us a net force in the same direction. So F net is just going to be those two forces added up. So I'm not going to use the negative sign. I'm just going to use the positive sign, the absolute value of that, because I know it's to the left. So it's going to be 8.42 times 10 to the 6 plus 2.78 times 10 to the 6, which gives me a total net force, 2.78, of 1.12 times 10 to the 7 newtons. And of course the direction is important. I know I didn't give you directions in this question, but let's assume north, south, west, east. So this is, the net force is to the west. Okay? So the thing that makes it a little bit more complicated than the gravitational force is just getting the directions right, making sure the directions make sense with your final answer. So when you're finding a net force, make sure that your free body diagram is accurate to the actual directions of the forces. So in this last question, I'd actually encourage you to pause the video and try this question yourself. I am going to go through the full solution, but you'll get more out of it if you try yourself. So pause it here, try it, unpause it, and see if you can come up with the answer. So I'm going to start off with a free body diagram, and we know that Q1 is our positive charge, Q2 is our negative charge, and Q3 is our negative charge as well, as a negative charge. So let's think about the direction of the forces acting on Q2. Between 1 and 2, there's going to be an attractive force, so they're going to be attracted together. So this is going to be the force between 1 and 2. It's going to be to the left, right? Q2 and Q3 are the same sign. They're both negative, so they're going to have a repulsive force. So the force there is going to be in this direction, right? Or you could draw the arrow on top. It doesn't really matter where you draw it for the free body diagram. So these are the two directions of the forces that are going to act on that particle. So we actually calculated these numbers in the previous question. The numbers are the same. So we know force 1, 2 is 8.42 times 10 to the 6 newtons, and we know the force 2, 3 is 2.78 times 10 to the 6 newtons, right? So how do we find the net force on Q2? Well, we need to add up these two forces. So to add up those forces, we can draw a triangle. We're going to do that force plus that force, and that's going to give us our net force, right? This is F net. Now, I'm going to give you a little trick here for doing this this algebra, make it a little bit easier. You know how it's 2.78 times 10 to the 6th? Just to do the algebra, we can take out that 10 to the 6th. The other thing you could do is you could just change the unit, because 10 to the 6th is called a meganewton. It's a million newtons is a meganewton. So you could just use it in meganewtons, and then you don't have to worry about that 10 to the 6th. Or you can just leave out the 10 to the 6th while you're calculating it, as long as you remember to put it back at the end. So I can actually just sort of assume this is 8.42. This is 2.78, right? We know that they're both times 10 to the 6th, but what that's going to tell us, the answer is going to basically be an answer times 10 to the 6th, and we just have to remember to add that 10 to the 6th in at the end. So for calculation purposes, if you want to leave that out, you can. So we can calculate that 2.78 squared plus 8.42 squared, square root of that. So basically, the length of F net, if you do the calculation, is 8.87 newtons. Oh, not exactly, times 10 to the 6. We can't forget about that 10 to the 6, right? Newtons. And you could put it here too. It's just when you're actually doing your calculator, you don't have to include the 10 to the 6. You'll see it'll come out to 10 to the 6 either way. And then the angle. And again, for the angle, you don't need to include that 10 to the 6 because the ratio of the sides is fine. It's the same. But if that's the angle we're trying to find, we use inverse tan of 2.78 divided by 8.42, and we get about 18 degrees. We'll round to the nearest degrees. So theta equals 18 degrees. So we can say the net force on Q2 is 8.87 times 10 to the 6 newtons west, 18 degrees north. There we go. So last reminder, just be careful about the directions of the forces, whether those two things are attracting each other or repelling each other.